So a very large plate of charge. We could call it a plane of charge as well. By very large, I mean we're going to work with distances close to it. So the electric field is going to be eta over 2 epsilon naught. I guess that's not written as a vector at the moment. So this charge, this plate, has a surface charge density of negative 50 nanocoulombs per meter squared. It's negatively charged. If I have an electron right here, it's also negatively charged. They're going to repel. So they're going to repel. If I let go of the electron, it's going to take off. I'd like to know how long it's going to take for the charge to move just a centimeter. Not very far, just a little tiny distance. How long will it take? And I don't imagine it will take very long. It's not a large distance to cover. So the whole reason the electron moves is because the electron is feeling a force. The force on the electron depends upon the charge of the electron and the electric field it is in. Force is directly related to the electric field. Any charge placed in an external electric field is going to feel a force. So let's find the electric field first. The electric field, just using magnitudes, we know eta is 50 nanocoulombs per meter squared, so 50 times 10 to the negative 9. We know epsilon naught is the 8.85 times 10 to the negative 12.
So wait, do you want to use negative or something in the direction you want to?
We're just going to go ahead and use magnitude at the moment. We can put the direction on it though. What direction will the electric field be in up here? Towards the plate. So negative j hat is the direction, according to our picture. One reason I was just writing it as a magnitude is because if all you have is the equation, the question in word form, we could have all drawn our pictures differently. But working our way through the math, we'd end up with the same answers. But according to the way I've drawn the picture, our electric field will be in the negative j hat direction. So there's an electric field pointing towards the plate. And by the way, there's an electric field towards the plate below it, but I drew the electron above it, so we only need to know the direction above. This electric field is constant as long as we remain close to the plate. As long as we don't get far enough out where that distance z starts to be comparable to the dimensions of the plate.
So does the electric field of the electron make any difference?
No, because it cannot exert a force on itself. So it does have an electric field, yes. But its electric field doesn't matter if we're looking at the motion of the electron, because it doesn't affect itself. If our electric field is constant, if this plate is very large, I'm assuming 1 centimeter is not big enough to make this equation not valid. Okay?
Is probably what we have to do.
Actually, we could, if we knew the dimensions of the plate, and so we knew what z was in relation to the dimensions, we'd be able to use the disk type equation.
I'm just saying, as it moves away,
But yes, that's true.
The value of the field is going to change.
That is correct. Okay, so the force. The force on our electron depends upon the charge of the electron. In this case, we do need to use the negative value. Times the electric field, which is in the negative y direction. Get a positive answer. meaning the force is in the positive y direction. So the electric field points down towards the plate, but the force on the electron is upwards. That's always the case. The force on a negative charge is always opposite the direction of the electric field. If the electric field is staying constant, then the force is staying constant. Okay? And we're fine within this 1 centimeter to assume that it's staying constant. Taking a little field trip back to the beginning of 2210, this force, if this is the net force acting on our charge, what does Newton's second law tell us? That's equal to the mass of our charge times the acceleration of our charge. Now, we could take into account gravity if you really wanted to. Force of gravity would be down.
It's so much weaker than this.
Yeah. But the mass of the charge is so incredibly tiny. It's 10 to the negative 31. If we just wrote it to 3 sig figs, we'd still have the same force. Okay? The force on the gravitational force is so incredibly much smaller than this that it doesn't have a noticeable effect. So mass. The mass of an electron, you can get that from the front cover of your book or off the test notes. Mass of an electron is 9.11 times 10 to the negative 31. So we can find the acceleration. Take our force, divided by the mass. The acceleration, because the force is upwards, the acceleration is also upwards. It's huge. Huge, huge, huge. It won't be able to keep this acceleration for very long.
It will approach the speed of light.
Yes, it will. And Newtonian physics goes out the window as you start approaching the speed of light. So we're not going to worry about that. The acceleration, though, is constant. The acceleration is constant because the force is constant, but the force is constant because the field is constant. So this acceleration, if the acceleration is constant, we can go back to our kinematic equations. We want to know how long it takes to go a certain distance. If we just go ahead and choose the initial position to be 0, it was released from rest, so the initial velocity is 0. So we can solve for time. If we bring the 2 over, divide by a, square root it, we're going to have the time. So x is 0.01 meters, a 4.96 times 10 to the 14th meters per second squared. Okay, I need mine in scientific notation. .35 times 10 to the negative 9 seconds. 6 nanoseconds. Very little time at all. Questions?